Hey everyone, let's dive right into this explainer. Today we're going to unpack the fundamental working principles of LED display modules. We're taking a pretty comprehensive training approach here, journeying all the way from the subatomic physics of a single photon right up to those massive full-color LED screens you see in stadiums, control rooms, and advanced virtual production sets.
Our agenda today covers 5 main areas. 1. Semiconductor physics. 2. RGB color mixing. 3. Shift registers. 4. Screen scanning. And 5. Refresh rates.
So, starting off with Section 1, Semiconductor physics at the microscopic level.
The absolute crucial phenomenon we need to grasp here is electroluminescence. It's actually fascinating. Instead of just dissipating excess energy as heat, electrons literally release it as photons of light. Inside an LED, which, remember, is essentially a PN junction, the diode's unidirectional nature means this electrical current flows precisely in one direction.
Think about exactly what's happening inside that junction. You've got an N-type material packed with electrons, right? And a P-type material full of holes where those electrons can fit. When unpowered, there's a depletion region acting kind of like a barrier. But when we apply a specific voltage, it forces those electrons in the N-type material to leap across that barrier into the P-type. And as they recombine with the holes, they drop from a higher energy level to a lower one, releasing tiny bursts of light, photons, as they go. Moving on to Section 2. RGB color mixing principles at the pixel level.
Okay, so the physical material of the semiconductor substrate literally dictates the exact wavelength of the light emitted. We aren't just slapping colored filters over white bulbs here. Gallium arsenide physically produces red light, gallium phosphide gives us green, and gallium nitride gives us blue. These are our essential independent building blocks.
By housing these 3 independent primary colors inside a single tiny diode unit, we create a full-color pixel. Because they're so close together, our eyes just naturally blend them. Using pulse width modulation, or PWM, we can rapidly toggle these individual diodes to vary their specific brightness. If you mix them at a precise white balance ratio, usually about 3 parts red, 6 parts green, and 1 part blue, we synthesize pure white light. And by adjusting those ratios, we can produce millions of distinct colors across the entire visual spectrum.
All right, Section 3, shift registers and latches at the circuit level.
So, what's the elegant answer to controlling millions of individual color diodes? It lies in the SIPO shift register. Think of a shift register as an incredibly fast, highly organized assembly line. It takes data arriving in a single-file serial format on just one wire and efficiently sorts it into individual, parallel delivery boxes from multiple LEDs simultaneously.
To visualize this, think of the clock pin, or CLK, as a constantly moving conveyor belt. The data pin, the SDI, is the actual package of ones and zeros being placed onto that belt. And the latch pin, or LAT, is the supervisor. So the clock pulses, moving data down the line one step at a time. Once all the data is perfectly lined up in the register for that specific section of LEDs, the latch supervisor hits a button, dropping all those packages into their respective LEDs at the exact same fraction of a millisecond. It's totally brilliant, allowing precise control of multiple LEDs with minimal wiring.
Which brings us to Section 4, screen scanning and multiplexing at the module level. Now, surprisingly, an LED video wall doesn't actually turn everything on at once. Instead, they use something called multiplexing. Specialized driver chips, often utilizing row decoders like the 74HC138, rapidly scan and activate specific segments line by line. So they flash on, then off, then the next row flashes on. This drastically reduces power consumption and the sheer number of driver chips you'd otherwise need.
But wait, if the screen is just rapidly flashing rows of lights, why doesn't it look like a flickering mess to us? Well, the answer is a biological phenomenon called persistence of vision. The human eye retains an image for roughly 1/24th of a second. If our LED module scans through all its lines more than 50 times per second, our biological hardware connects the dots for us, and our brains perceive it as a single, perfectly continuous, solid image. And finally, Section 5, refresh rates and performance at the human and macro level.
So, the refresh rate is just how many times per second the screen updates and redraws its image. A basic screen might refresh 300 to 1,000 times a second. That's totally fine for a static billboard, but for video, it causes eye fatigue, motion blur, and if you point a camera at it, you're going to see those really ugly black scanning lines. On the other hand, high-end display refreshing at 1920 Hz, 3840 Hz, or even up to 7680 Hz ensures absolute broadcast quality perfection. Motion is completely fluid, and cameras pick up a flawless, solid background. This is exactly what makes modern virtual production and XR studios possible.
But
Achieving those massive refresh rates requires top-tier physical hardware across the board. We're talking advanced dual-latch PWM driver chips, robust interfaces like the standard HUB75E or the HUB320 for high-density modules to seamlessly link the receiver cards. You also need crucial auxiliary components like the 74HC245 chip for signal amplification, plus some serious power supply designs to prevent thermal throttling. Basically, every single piece of the puzzle absolutely must be optimized.
It is truly mind-blowing when you step back and look at a real-world naming convention on a module, say P32121 64x64 32S V1.0. You're literally looking at a masterclass in modern engineering. That string means a 3mm pixel pitch, a 2121 diode size, a 64x64 resolution, running at a 32 scan rate as a surface mount module, version 1.0. It all starts from the subatomic leaps of electrons in a p-n junction, gets sorted by shift registers, multiplexed across rows, and then refreshed thousands of times a second just to trick our biology. It perfectly scales up to create the digital world around us, which really leaves us to wonder, what impossible visual experiences will LED technology power next? Thanks so much for joining this explainer, and keep exploring.